Congratulations, you've mastered limits. Now what? Today, we're going to put a different slant on slope as we use limits to calculate instantaneous rate of change instead of average rate of change. This is called a derivative, and it is the meat portion of the meat and potatoes of calculus. It's time to earn another well done as we explore derivatives, starting now. And welcome back. So, before we go into calculating derivatives, first we should probably answer the question, what is a derivative? Well, there are several ways to define derivatives. My sort of layman terms for it is I define a derivative as the instantaneous rate of change. Basically, the velocity of something at a moment in time instead of between two periods of time. You can also think of a derivative as the line that's tangent to the curve of your graph. So one important thing to note about derivatives is that the steeper the curve, the greater the rate of change. So if a curve is very flat, the derivative is going to be close to zero, which means the rate of change is very small, and a steeper curve is going to have a greater rate of change, which means that the derivative is going to be a much higher number. When you're encountering word problems, I would highly recommend keeping an eye out for some of these terms. If you see the word derivative or slope or tangent line or rate of change or velocity, all of these words tip me off in a word problem to use the derivative. So before we actually get into derivatives, again, let's do a little bit of slope review because that's what, a derivative is based off of. So a lot of you are familiar with the rise over run convention of slope, and the mathematical formula that was used to calculate it is y2 minus y1 over x2 minus x1. Well, today we're going to do a little bit more mathy way of writing that same thing. It's going to be f of b minus f of a over b minus a. F of b being a y value, f of a also being a y value, b and a are x values. So let's go ahead and draw this graph, and you'll notice the blue curve, it's very similar to x squared. And the point that we're going to choose there sort of randomly is x comma f of x. So any x value, any y value, it just so happens that ours is at 0, 0. It's just for easy explaining. So what we're going to do now is we're going to add some amount h to x, and we're going to use that point, we're going to plug it into our function to figure out the y value, and we'll call that x plus h comma f of x plus h. And we're going to figure out the slope between the 2 points. F of x plus h minus f of x all over x plus h minus x, just like BA. So now the denominator there can simplify into just h. And if we erase all those points to make it a little bit easier to see, what we can do now is take h and make it smaller and smaller and smaller. What the idea is we want to get the 2 points distance away from each other to equal 0. And how do we do that? Well, we use a limit. And this is the definition of a derivative. So what you're going to do is you want that distance between your 2 points to equal 0. So let's go through an example problem, shall we? What is the derivative of f of x if it is equal to x squared plus 2x? Well, let's start with the formula that we just figured out. It's the limit as h approaches 0 of f of x plus h minus f of x over h. F of x was stated in the problem, it's x squared plus 2x, and f of x plus h, well, we just substitute that for x, and we get x plus h squared plus 2x plus h. So let's go ahead and plug all those things into our formula. I like to use brackets to kind of keep everything together. I think it's a little bit cleaner. Do note something very important about the x plus h there. It is not x squared plus h squared, you do not distribute that square, you have to FOIL. You end up getting x squared plus 2xh plus h squared. If you don't believe me, go ahead and work it out yourself. And let's go ahead and start simplifying the problem a little bit. We plug that number back in. We distribute the 2 to the x and the h, and we get 2x plus 2h. And we distribute that negative to the x squared and the plus 2x. So we get negative x squared and negative 2x all over h. So one of the most important things when you're calculating a derivative by hand is making sure you keep your work very neat and organized. What we're going to do right now is we're going to cancel out some of the like terms. So you'll see an x squared and an x squared and a 2x and a negative 2x cancel each other out. And we end up with the limit as h approaches 0 of 2xh plus h squared plus 2h all over h. So what you'll notice is they all have an h in common there, so we could effectively factor out the h and cancel them out. We're just going to cancel them from each of the terms, and we end up with 2x plus 2 plus h. So just a little bit of reordering there. Now what we can do is take the limit as h approaches 0. So essentially substitute the 0 in for h, and what you end up with is the derivative. And one way to write a derivative is using that funny little marker in the top right corner there. It's called a prime. So f prime of x is equal to 2x plus 2. And sometimes in a problem, for a little bit of a bonus here, what they'll ask you is something like, what is the slope at x equals 5? Well, do recall that when we're being asked for slope, what we should do is take the derivative, and what we're going to do now is plug 5 in for the x value. So little quick calculation there, we find that our slope is going to be 12. And how that would kind of look there in just sort of a crude drawing, you'd see the blue line represents the derivative of the graph, and at that little dot right there, x equals 5, we find the slope is going to be 12. The y value, what you would have to do is plug it back into f of x, not f prime of x. So that's derivatives in a nutshell. I hope you all enjoyed that, and I will see you guys next time.